Let's take a look at how we can use the limit definition of a derivative to find the derivative of a constant function. So we are going to assume that f of x is equal to some constant. Our limit definition of the derivative is here for our reference. So let's go ahead and get started. So we want to find f prime of x, assuming f of x is equal to c. So that's going to be the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So let's go ahead and evaluate our function. So we have the limit as delta x goes to 0, f of x plus delta x. So in my function, everywhere there is an x, I'm going to replace it with delta x. You'll notice that there is no no x in the definition of the function. So I cannot replace x with delta x. In other words, our function just remains c minus our original function, which was defined as c, over delta x. So that gives us the limit as delta x goes to 0 of 0 over delta x. Now, keep in mind that as delta x goes to 0, those are non-zero values of x. So, for example, x could be 0.1 and then 0.01 and 0.001 and so on and so forth. So our denominator here with this delta x is a constant. It is a non-zero value. So we can simplify 0 over delta x, and that actually simplifies to be 0. So we have the limit as delta x goes to 0 of 0, which is going to give us 0. Because as delta x approaches 0, 0 does not change. It remains 0. So for f of x equal to c equal to some constant, any constant, f prime of x will be 0. So let's do something similar. Let's use the limit definition of the derivative to find the derivative of the exponential function. That is, f of x equals e to the x. And we have here the limit definition of the derivative for our reference. So let's go ahead and get started. So we want to find the derivative of our function e to the x. So our derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Now, referencing the function we've been given, we'll have the limit as delta x goes to 0. In our exponential function, we will be replacing our exponent x with x plus delta x in the first part of this numerator. So e to the x plus delta x minus the function itself, so e to the x, all over delta x. Now, as delta x goes to 0, both our numerator and our denominator are headed to 0. So we need to use some algebra to help us simplify things up here a little bit. So one thing that we can do is there is a property of exponents that says that a base to a power that is a sum, that is b to the m plus n power, is equal to b to the m times b to the n. So we're going to use that property on our exponential function right here. So this is going to be the limit as delta x goes to 0 of e to the x times e to the delta x minus e to the x over delta x. At this point, we can see in our numerator that there is a common factor of e to the x. So we can use the limit as delta x goes to 0 of e to the x times e to the delta x minus 1 all over delta x. Now we're going to leverage a property of limits. You'll notice that e to the x is not a function of delta x. So as delta x goes to 0, e to the x remains constant. So we're going to factor out the e to the x as it is a constant with respect to the limit as delta x goes to 0 of e to the delta x minus 1 over delta x. Now, at this point, we're going to take advantage of a property. This is a limit that you could prove for yourself. We're just going to leverage it as part of showing what the derivative of the exponential function is. And that is that the limit as delta x goes to 0 of e to the delta x minus 1 over delta x equals 1. So using that knowledge, then we get e to the x times this limit equals 1. So e to the x times 1 is simply e to the x. So the derivative of the exponential function e to the x is actually the function itself. And it's the only function that has this property where it is its own derivative. I hope this helps.